All right. Hi, everybody. Welcome back. Hope you had a good weekend. And so last time we did a little bit of root systems and generalized some properties of permutahedra, which, by the way, I forgot to discuss the proofs. So maybe let me just briefly write down the facts again. So one was that the permutahedron of rho is the one half the sum of line segments corresponding to all positive roots. And the other fact was that the same thing is the sum of the root system hypersimplices, which are just the permutahedra corresponding to the fundamental weights. Right? So, and I said that these were true, but how do you prove them? So give me a proof idea for each of these facts. Okay, the roots form a basis. So, well, I mean, the simple roots form a basis. Okay. Oh, so you're saying the roots? No, but like for instance, for the even for the usual permutahedron, the roots are of the form. So for pi n, the roots are of the form ei minus ej, but the vertices are permutations of 1 to all the way up to n. So these are, you can't really say that the roots are extremal because they are not even vertices. But it's, I mean, it's a good idea. You have to somehow say that one vertex of this guy has to be a vertex, right? Some point has to be extremal for this. Which point would that be? Rho. Oh, okay, right. So, okay, yeah. So indeed, if you try to maximize the dot product with the rho, let's say, then I mean, it takes some time to actually figure out that. But I mean, it is. It takes some work to figure out why rho has to be a vertex of this guy, but basically, rho is a vertex of each of these polytopes. Because rho is the sum of positive roots, and it's also 1/2 the sum of positive roots, and also the sum of the fundamental weights. So for each polytope on each side of these equations, rho is a vertex. And then what do you do next? Oh, okay, nice. And then you basically act by the while group, and then you're done. Because each side is invariant, and but yeah, basically the same idea works for arbitrary root systems, and that's it. There is no, I mean, I don't know any other facts of this form. So root systems are a very natural framework for these statements like this. And by the way, there was another statement, which is the one skeleton of the permutahedron was supposed to be equal to to what? That's the diagram of what? Okay, nice. So the one skeleton of the bromidahedron was equal as a graph to the Hasse diagram of the weak Brouillard order, and turns out that it also generalizes to root systems. It equals to the Hasse diagram of the weak Brouillard order on W, on the Weil group. So, and I haven't defined the weak Brouillard order on W, but it's basically, it's a very natural generalization of the symmetric group. So if you have alpha 1 through alpha r simple roots, then W is generated by S alpha 1 through S alpha r. So in principle, it's generated by all simple reflections for all roots. But it turns out you can only take simple roots and then they generate the whole group already. And in particular, you can define the, so for W, a sort of generalized permutation, right, an element of the Weil group. You can define the number of inversions. There's no inversions here, but you can still define the length, which generalizes the number of inversions as the minimum number L, the minimum, let's say M, such that W is a product of M simple transpositions, simple reflections. Si1, Si2, well, S alpha I1, S alpha I1, S alpha I2, all the way up to S alpha IM. Okay, so you try to find the minimal length expression for W in terms of these transpositions, and then the number of those is going to be the length. So, and it's an exercise to check that for Sn, right? When your root system is of type A n-1, L of W is just the number of inversions. And in particular, you can define the weak Brouillard order by the same sort of rule that V is covered by W for V and W in your Weil group. V is covered by W if W is obtained from V by multiplying by a simple reflection, and the length of W is the length of V plus 1. So you notice that this looks almost literally the same as in type A n-1, but I have to slightly alter the notion of the length, which is also very natural. So there's the weak Brouillard order and there's the strong Brouillard order for arbitrary root systems. And so yeah, all these facts. It is one thing that is not true for arbitrary root systems is that the bromidahedra do not tile the space. If you remember, let's say the plane can be tiled by copies of bromidahedra of type A2, which are the hexagons. You can tile the plane with the hexagons, but it cannot be tiled by octagons. If you take type B2, you try to tile the plane with octagons, and then you fail. So I don't think I mean, I tried to Google, maybe there is some other kind of interesting, maybe I should take another pentahedron of a different point or something, but yeah, I couldn't find any results for arbitrary. I think it's just false. Any questions so far? Because I'm gonna, no questions. All right, so in general, I'm gonna tell you, we're gonna have a class, I'm gonna tell you a whole bunch of nice things, nice statements about different things in type A, and you're welcome to try to find generalization for arbitrary root systems or ask me about them. Most of the time I'm gonna say, I don't know, but still it's always very natural to ask what's the root system version of some statement. So anyways, if there's no questions, let me go to the next topic, which is gonna be I'm gonna mention some general properties of polytopes. So far, we only dealt with very special polytopes, hypersimplices, pentahedra, things like that. And now I want to, because you can do more things with these special polytopes if you know some general story about arbitrary polytopes. So that's what I'm going to try to do, and these are very fundamental to all polytopes. And I'm going to start by talking about the face lattice. Let me introduce a few definitions. First of all, let's say you have a PO set. A PO set. Let me call it L. Right? It's just a set with a binary relation, which is transitive, etc. And then I'm going to say that it is bounded if there is a unique maximal element and a unique minimal element. Maximal element, which is going to be denoted 1 hat, and a unique minimal element, which is denoted 0 hat. In the Hasse diagram, 0 hat is somewhere here, 1 hat is somewhere here, and then the whole PO set is between these two. And that's one definition. And another one is that L is called a lattice. So for a lattice, what you want is that whenever I have two elements, x and y, then there should be a unique upper bound, well, a unique minimal upper bound and a unique minimal lower bound. The upper bound is denoted x join y, and the lower bound is x meet y. Formally, L is a lattice if for all x comma y in L, there exists a unique upper bound, which is z in L, such that x and y does not equal to z, a unique minimal z, such that this is true, and denoted x, well, z is the join of x and y, and there is also a unique maximal lower bound. Z in L, that z is less than or equal to x and y, denoted x meet y. All right. Any questions on the definitions? Let's try an example. Let's say I try an example. Let's say I take the weak Brouwer order. On, let's say, S2. One, two, three, 2, 1, 3, 1, 3, 2, 3, 1, 2, 2, 3, 1, 3, 2, 1. So, question: is this a lattice? Okay, I see thumbs up. So this thing is a lattice. So let's say if I take any two elements, let's say 2, 1, 3 and 3, 1, 2, then there's a mid, which is 3, 2, 1, and then there's a join 1, 2, 3. If my two elements x and y maybe look like this, 2, 1, 3 and 2, 3, 1, then the mid is this guy and the join is, so pretty easy. And actually, so an interesting fact, which is that this holds for the weak Brouwer order for arbitrary n. So an exercise, which is, I think it's pretty hard. Maybe it's going to be in the homework or something. Try proving. And let me try another one. Let's say another example, maybe I take the strong Brouwer order, which, do you remember how it looks like? Yeah? Okay, this with an X. Thank you. So, is this a lattice? Yeah? No. Why not? Okay. Okay, so indeed, if I take 2, 1, 3 and 1, 3, 2, then they have the upper bounds 2, 3, 1 and 3, 1, 2, which are incomparable, right? And there is no unique minimal upper bound. So not a lattice. And again, for arbitrary n, the strong Brouwer order is not a lattice, but the weak Brouwer order is a lattice for some reason. Exercise. And so a lattice is a pretty useful thing for us because it's going to help us study faces of polytopes and how they are glued to each other. So let's say I have a polytope. Then the face lattice, which is denoted L of P, is the whole set of faces of P, which are ordered by inclusion. Or by containment. Basically, one face is smaller than another one if and only if it's contained the other one. All right. So if I take all such faces, then do I even get a poset? Is there transitivity? If this is less than this, less than some other f double prime, then of course f is contained in f prime, contained in f double prime. So it's easy to check that all the axioms of a partially ordered set are true for the face poset. But the question is, why is this L of P a lattice? Let's say, is it bounded? What's the minimal element? Okay, the minimal element is the empty face, and the maximal element is the whole polytope. Okay, nice. Why is it? Why do any two elements have a meet? Oh, intersect all the upper bounds. Wait, hold on. It's if you intersect. Oh, okay, yeah, but that's interesting. So if you, right, let's say f and f prime are two faces. So what is f meet f prime? Which meet means it has to be smaller than each of them. Yeah. Oh, yeah. This is subset equal is contained. Yeah. Intersection. Right. So the meet of two faces is the maximal face that is contained in each of them. So that's just the intersection. And it turns out that, well, I mean, you can ask the same question for the join. And it's sort of, I mean, you can say that it's the okay, nice, thank you. So it's the intersection of all f double prime, which contain both f and f prime, which is also a face. Yeah, it's the same as, well, I mean, it's not quite the convex hull, right? Because if you, maybe if f is this edge and f prime is this edge, then you take the convex hull, you get some part of the face which contains both of them. So, yeah, this definition works fine. And it turns out that in general, if you have any two of these three conditions, then they imply the third one. So it's enough to check, let's say that if you have a poset which is bounded and any two elements have a unique meet, then it turns out that it just follows by sort of the same. There are some sort of, you can write some meet of a bunch of things over here, which the meet of a bunch of things which are greater than each of them. You can check that what you get is always a lattice. Yeah, well, yeah, I think it has to be finite. I'm not actually sure. It could be that it works for infinite. Oh, okay, you're saying no, but it's not. It has to be bounded, right? Oh, you're saying, yeah, maybe it has to be connected or something. Yeah, I don't remember, but I think for finite it definitely works. All right. So now with the help of this definition, we can define when are two polytopes combinatorially equivalent. Because before, so remember, call that P and P prime are finally equivalent if there exists a linear and affine map which is bijective. Right? So, and this turns out that this notion is a bit too restrictive for us combinatorialists, right? Because, so for example, maybe a regular square is not finally equivalent to some trapezoid. But it has the same combinatorics of all faces. So sometimes we like to talk about the two polytopes being equivalent if they have the same combinatorics. So two polytopes P and P prime are combinatorially equivalent if, wait, infinite chain is itself a lattice. Why would it not be a lattice? Oh, you're saying, okay, these two do not imply bounded. All right, cool. Yeah, that's good. Combinatorially equivalent if their face lattices are isomorphic as both sets. So there is a bijection between which sends the faces of this guy to the faces of this guy, preserving the order relations. And so maybe, all right, so maybe I should, let's say I try, let's just take one, maybe I take the square, and I label the vertices 1, 2, 3, and 4, and then I want to draw the face lattice, which is going to look, see, face lattice looks like this. Empty set, there's 4 vertices, 4 edges, and there is the whole polytope. So that's my face lattice, and it's the same as if at any quadrilateral. So I kind of disregard the geometry. All right, now let me make one more definition. Let's say if I have any partially ordered set L, then I'm going to define what is called the opposite pole set, which is going to have the same set of vertices, but it has the opposite order relation. It's defined by if x is less than y in L, that happens if and only if y is less than x in the opposite order. All right, so you just flip your pole set upside down, and then maybe if I flip this guy upside down, I get an, turns out here I'm going to get an isomorphic lattice. And of course, if you have a lattice and if you turn it upside down, it's still a lattice, right? Because the mid becomes the join and the join becomes the mid. So how is this operation relevant to polytopes? What happens if I start with a polytope and then I take the face lattice and I turn it upside down? P is a polytope. Then the opposite of the face lattice is, I wonder if somebody can guess. Yeah? Nice. Oh, okay, nice. Yeah, very nice. Yeah, that's correct. So the opposite of face lattice is, it turns out to also be, is also the face lattice of a polytope, which I'm going to denote by P star, called the polar dual. polar dual of your original polytope P. And if you've never seen this before, then it should be puzzling to you. This is first I take the polytope, then I forget the geometry, and then just take the combinatorics, and I flip it upside down, so each vertex has to become a facet, and each facet has to become a vertex. It sounds kind of weird that this operation should, like for high-dimensional polytopes, it's unclear how to. The question is how to define P star. And so to define it, I'm going to need to make a couple more definitions, so, which are also very useful. So first of all, if you have any subset P of R to the D, what you should think of is maybe the permutohedron or something that lies in a hyperplane, or maybe in some lower dimensional linear subspace. And so in particular, yeah, maybe I have R3, and then maybe P is the simplex. Right? Then, so let's say, what is the topological interior of such a polytope? As a subset of R to the, yeah? An open ball of dimension D minus 1. Okay, that's a very interesting point. What is the definition of an interior? So let's say I have a topological space, and then you have a subset. Its interior is what? Oh, empty. Oh, interesting. Why is it empty? Okay, nice, interesting. Right. So by definition, the interior of this triangle would be the set of points which are contained in P together with a small three-dimensional ball around them, which there is no such points. The triangle is flat. And so you still want to talk about the interior of a polytope, even though it's embedded in a higher dimensional space. So that's why we call it the interior P is empty. But we want it to be the two-dimensional open triangle, and that's called the relative interior. P is the interior of P. When I talk about the interior, I have to specify the ambient space as a subset of the affine hull. Do I call it affine span or affine hull? Never remember. Right. So you take the affine span, which is here is going to be a plane, and then you take all points which are contained together with like a two-dimensional ball inside P. All right. So in particular, you can always, if you have any polytope, you can always will assume so after maybe some shift of coordinates, always will assume that 0, the origin belongs to the relative interior of P. So in this example, you'd have to shift the origin to inside the triangle somewhere. And so assuming that, it's pretty easy to define P star. Definition, assuming this, let P star be the set of all vectors in the affine span. Well, we can even assume that let me even assume assume that the dimension of P is D. So let's assume that P is full dimensional for now. P is inside R to the D and is full dimensional. Then P star, by definition, is set of all points in R to the D, or in the affine span of P, such that the dot product of X with Y is less than or equal to 1 for all Y in P. That's the definition. And let me try one example. Okay. So maybe 1, 1, -1, -1. So and one important point here is that this definition, the result depends very heavily on where the origin is in your polytope. You're going to get different, geometrically you're going to get different polytopes. But let me just choose the origin here, and then let's say my polytope P looks like this. All right, so then I want to find the dual. What is the dual of P? First of all, what's the shape going to be? Also a triangle. Okay, how do I find its vertices, let's say? Because see, this is, here I have, this looks like an H polytope, right? Because I have inequalities, but I have infinitely many inequalities. So how do I find? Okay, so you want an inequality. Let's say here, for this vertex, the inequality is going to be, what is it, x1. So let's say this is x1 and x2, right? And then x1 should be less than or equal to 1. All right, nice. I have 1 here, and then x1 less than or equal to 1. All right. And then I do maybe this vertex here, which is going to give me x2 less than or equal to 1. And then what's the other inequality? X1 plus x2 is greater than or equal to 1. Oh, okay. So you want it to look like this, right? Wait, hold on. It's maybe -1. Yeah, that's better. Let me try -1. Because, yeah, it's minus x1 minus x2 should be less than or equal to 1. Has to be a -1. And so let's see. -1, -1. Yeah, so my polytope here is going to be contained. This is P star. So each vertex of P gives me a facet of P star. Somehow it's normal. The corresponding vector is normal to the facet of P star. And turns out it's vice versa. This is 1, 1. And this is, yeah, so this face corresponds to this vertex here, and etc. So, and that's a theorem which they try to state it here. So let's say I have a polytope in RD, full dimensional, containing the origin in the relative interior. Then the claim is that the face lattice of P the opposite of the face lattice of P is the face lattice, is isomorphic to the face lattice of the dual of P. So that's one point, and I have to specify a bijection. This offset isomorphism means there is a bijection between the faces of P and the faces of P star. So what is this bijection for each face of P? The corresponding face of P star is what? Can somebody guess? If I have a face of P, what's the dual face of P star geometrically? I'm going to denote it by F diamond, or because yeah. Anyways, what is it going to be? Yeah. Oh, okay, interesting. So there is one idea, which is to take F star to be just the corresponding face to be just F star, which is the set of all x in R to the D, such that x comma y is less than or equal to 1 for all y in F. And well, there's one problem with this, namely, if you take a face of P, then it usually does not contain the origin. That's sort of a problem. And yeah, maybe let's see what happens if I or even let's say if I take this vertex, then the corresponding F star would be the whole half plane here, right? It's just I'm just going to have one inequality this form, so I'm going to get the whole half plane. So this is a very natural guess, and it doesn't work, and that's why I need a different notation. Any other ideas? Yeah. Which have constant inner products on F. Oh, okay, interesting. So you want all vectors, let's say, in P star, which have x and y is constant C for all x in F. Oh, so you want constant to be equal to 1 for all, okay, y and F, all right. Okay, that sounds plausible, right? What is the constant? I mean, depending on the constant, you're going to get, let's say, if your F is here, then depending on the constant, you're going to get different slices of your P star. Right? Which one of them is the face? Say it louder. Should be 1, as I suggested. Interesting. So yeah, and it turns out that that's the correct definition, even though it's sort of unexpectedly that you should just put 1 here for all of these y's. But it turns out it actually works, right? So you can, for instance, let's say you take this face here, x1 plus x2 is equal to 1. And the corresponding dual face is this vertex here, and you can check that. So the dot product with 1, 1 of any of these points is equal to 1 on the nose. Yeah. So if you intersect it with, well, it's contained inside P star, right? P star it has strictly more inequalities than star. So you get the entire half plane to the left of this line, right? Because it's just this inequality here. But you can, so if you make this an equality, then you can intersect with P star, and then you're going to get this dual phase descent. All right, yeah, maybe I should give some examples. And I'm just going to name a polytope, and then you are going to tell me its dual. Examples. Well, it's a blitz. So let's say I take the dual of a simplex is simplex. What? Simplex, okay. Should I write that it's combinatorial equivalent or equal, or it's what should be the equivalence relation here? At least combinatorial equivalent. Okay. Yeah, and actually, because the simplex does not contain the origin, I can't really speak of the dual until I at least modify it in some way, like shift the origin somewhere. So you can't really talk about a fine equivalent, even though actually, if you shift the origin, these are going to be a fine equivalent. Fine. Anyway, yeah, the picture here is tetrahedron corresponds to the upside down tetrahedron. Okay, what's the next one is, let's say I take the cube and I take the dual. What am I going to get? Let's say in 3 dimensions. Octahedron. Cube is dual to the octahedron. And what is this in general? Oh, okay. So you want it to be some hypersimplex here. Well, actually, I don't think it's true. Actually, it turns out that the answer is the convex hull of all plus or minus basis vectors. I between 1 and n, 1 and d. And that is called the cross polytope. So it's a nice centrally symmetric polytope. Instead of the simplex where you take only the basis vectors, you take plus or minus the basis vectors, like for the octahedron here, and then you get the cross polytope. And it's dual to the cube. And all right, so what about maybe I take the icosahedron? And I take the dual. Does anybody know the icosahedron? It's, I don't think I can draw it, but it looks sort of. What's the dual of the dodecahedron? Dodecahedron. Nice. And etc. So the dodecahedron, it has these pentagonal faces. And this has 20 vertices. 20 vertices. This has 20 faces, facets. This has 12 facets, I think. This has 12 vertices. So yeah. Anyways, this is something you've seen in high school, right? Like all these Platonic solids are dual to each other, but actually this works in arbitrary dimensions. There's no Platonic solids anymore, but you can still take take duals of polytopes. So yeah. 20 faces. Oops. No, sorry. Is it true? No, I think it has 20 faces. All right. Okay. That's few vertices. Facets. Thank you. All right. Any other questions? Yeah. Okay, so you want polytopes which are self-dual and like the simplex. Then I have to think about it. It could be that there's, yeah, I have to think about it. I can't remember on the top of my head, but it's a very nice question. Yeah. Well, the middle of each face is not quite. You want to take each, like the barycenter of each face. I don't think it works quite. So, I mean, you have to define the center in a certain way, and I think no matter how you define the center, it's not gonna. Yeah, because when you take the dual, if you have, let's say, a vertex of high degree, then in the dual polytope, the corresponding vertices have to form a face. They all have to lie in the same hyperplane. And if you move these points slightly, then you can kind of make these centers of mass to not lie on any plane. Yeah, you have to use that construction. That's an interesting question. I think the answer is no, but I don't know. Yeah, I think the only construction I know that actually works is that construction.
When we define polytopes, are they?
Yeah, polytopes are convex halves of finitely many points. Any other questions? All right. Yeah, thanks. See you on Wednesday.